Good. So today, then, I want to just take a step back and motivate why the hypergeometric equation is both interesting and important. Okay, and the example comes from quantum mechanics, and in fact, the quantum mechanics of vibrational excitations of molecular systems. So, you know, the study of molecules is really what chemistry is all about. And in particular, understanding what happens with molecules when you excite them and they relax to their ground state again is an important part of essentially much of chemistry and some of scattering physics. So, for example, understanding the color of clouds, the color of the sky, all comes from understanding molecular systems and their vibrational excitations. So, one of the early systems that was solved was what we call the Poiseuille-Teller system. And it was solved because it's essentially an exactly solvable problem. And it turns out it's also related to a number of other interesting systems like supersymmetric quantum mechanics and things like that. So the statement here is that vibrational excitations of molecules can be modeled by the following potential. So the Poiseuille-Teller potential in which we consider the quantum mechanics of a particle moving in a one-dimensional potential V of x equal to 2 cosec squared x minus 1, with x an angular variable that lies between 0 and pi, is used in modeling molecular vibrations. Okay, so as I said, it's an example of an exactly solvable quantum system. So the Schrodinger equation that's related to it. So the Schrodinger equation in the quantum mechanics that we would try to solve here is minus the second derivative of the wave function psi by x squared plus this potential 2 cosec squared x minus 1 times psi equals energy times psi. Okay, so this Schrodinger equation is exactly solvable. And exactly solvable systems in quantum mechanics are pretty rare. And so whenever we get them, we tend to study the hell out of them and try to see, as how much we can actually learn from them. So things like the harmonic oscillator, the free particle, are these archetypical problems that constantly come up. And so it's worth stopping, spending a little bit of time and understanding this problem. if for no other reason than the fact that it is an exactly solvable system. So what does it mean that is an exactly solvable system? Well, there are two ways to think of this. One is, what we have here is a second order differential equation. And an exactly solvable system like this, with a second order differential equation, means I can actually solve the differential equation and get a closed form solution for psi, for the wave function. Okay. Now, looking at this cosec squared in there should at least, if it doesn't instill fear in you, it should at least give you some pause, because, you know, things like trigonometric functions sitting in coefficients of differential equations are not typically what you would go to if you wanted to think of a solvable system, an exactly solvable system. However, my claim is that it is, and I'll show you how we're going to do that just now. So that's one way of thinking. The other one is that this particular differential equation, the Schrodinger equation, the Schrodinger problem, is of the form Hamiltonian acting on vector psi. It's a vector in a Hilbert space, a continuous function space, is equal to number times that same psi. So it's an eigenvalue problem. So another way to think about this as a solvable system is I can actually solve the eigenvalue problem. So what does it mean to solve an eigenvalue problem? Well, you solve an eigenvalue problem when you solve the eigenvalues, you solve for the eigenvalues, and you use that to determine the corresponding eigenfunctions. Or vice versa. You know the eigenfunctions, you can solve the eigenfunctions, and then use that to determine the eigenvalues. In this case, the eigenvalues are all the possible energies that this vibrating molecule can take. Is that clear? Anyone? I'm going to call on names as representatives. Okay, very good. Okay, so our goal now will be to try and solve this problem, and we want to try and solve the problem as a differential equation to start off with, and then we'll return to the differential equation and pick up where we left off last time, trying to solve it more generally for the associated differential operator. All right. So having laid out what we're planning on doing, let's go ahead and do it. So I have a differential equation in psi and x. It's a one-dimensional ordinary differential equation, so it's not that daunting, but nevertheless, it's still got this trigonometric function in it that I'm a little bit wary of. So the first thing I'll try and do is get rid of the trigonometric function in a way that makes the coefficients of this differential equation polynomial. So to do that, let's start by making a change of variables. We're going to change variables from x as our independent variable to a new variable z. So from x to a new variable, which I'm going to call z, and I'm going to use yellow to just distinguish it here, and I'm going to define z as sine squared of x over 2. Now, what I typically get asked by students, whenever I do problems like this is, how the hell am I supposed to know to pick sine squared x over 2? The answer is typically years and years of experience. When you work with more and more of these differential equations, you get to see patterns, and you get to see what guesses for changes of variables are useful. In the same way that, when you first encounter change of variables, when you're trying to do integrals, I'm sure it must have seemed pretty foreign back then as well. But then if you think back on it, you'll realize that you got better and better at it, at picking the appropriate variables by doing more and more examples. And so, the first people to solve this equation, this Poiseuille-Della equation, realized that here was a good guess to make to convert the problem from a trigonometric problem to a polynomial one. So I want to change variables from x to z. So that's my independent variable, and I want to write psi, which remember was a function of x, and x is now a function of z. So psi is a function of z, and I'm going to write psi as z minus 1 over the square root of z times a new function phi of z. So I'm going to change independent variables from x to z, and I'm going to change the dependent variable from psi to phi. Okay, so notice that with this change of variable, also comes a change of the domain. So where x went from 0 to pi, z is now going from 0 to 1. Okay, so if I substitute this into the Schrodinger equation, I get the following. We'll find that the coefficient of the second derivative term is z times 1 minus z. So that's d2 phi by dz squared plus minus a half minus 2 z d phi by dz minus 3/4 minus e, I'm bringing the energy onto the left-hand side, times phi. All of this is equal to 0. So this is the form of the Purcell-Teller Schrodinger equation once I've made my change of variables. Now, if you think back to what we started off talking about last time, this is nothing but a hypergeometric equation with a particular choice for the coefficients. So compare this to the hypergeometric equation. Let me use a different color. So compare this to the hypergeometric equation, z 1 minus z d2 phi by dz squared plus, last time we said gamma, minus alpha plus beta plus 1 times z phi, sorry, d phi by dz minus alpha beta times phi equals 0. Okay. If we make the identification, so this is the hypergeometric equation. That we wrote down the last time. And the comparison holds as long as we make the identification identifications that alpha is half minus square root of 1 plus e. Beta is a half plus the square root of 1 plus e. And gamma is minus a half. So if I make these identifications, then the equation that I have starting from the quantum mechanics problem is nothing but a hypergeometric equation, right? And if in addition, we write take as a definition the parameter k to be the square root of 1 plus e, which I don't want to be carrying around, then the general solution to this equation is given by phi of z equal to some constant, let's say a, times a function, which I'm going to write as 2f1. So this function has two subscripts there. And the notation 2f1 comes from this function being a specific form of a more general type of function called Pochhammer functions. But we're interested in one specific example of those functions called a hypergeometric function. And the hypergeometric function 2f1, it's not the only notation you'll find, but because I'm using phi for something else, I'm going to stick with what is more or less standard notation. Has 4 variables. In fact, it has 3 parameters and 1 independent variable. The 3 parameters are a half minus k, a half plus k, the same k we just defined, minus a half, and independent variable z. And you'll notice that a half minus k is the parameter alpha, a half plus k is the parameter beta, and minus a half is the parameter gamma. So in general, hypergeometric functions, 2f1, are functions of the 3 parameters in the hypergeometric equation, together with the variable, the independent variable z in the equation. Of course, this is a second order differential equation, and so you should expect 2 linearly independent solutions. And the second solution is some constant b times z to the 3 halves times 2f1 now of 2 minus k, 2 plus k, 5 halves, and z. Okay, and I use the colon to distinguish between the parametric dependence, the alpha, beta, and gamma, and the actual variable dependence z. Okay, so let's unpack this, because there's a lot to unpack. A and B here are integration constants. I have 2 integration constants. I should expect 2 integration constants because this is, after all, a second order differential equation. So these guys are integration constants. there are two linearly independent solutions, the one that multiplies A and the one that multiplies B. And of course, the general solution to a second order linear differential equation, second order differential equation is a sum of these two. These functions 2f1 are called hypergeometric functions, and hypergeometric functions by definition are solutions of the hypergeometric equation. And the reason they're called hypergeometric functions and is because they solve the hypergeometric equation, but actually you can turn that around, and the hypergeometric equation is the thing that is solved by hypergeometric functions, and these hypergeometric functions are generalizations of the standard geometric functions that you're familiar with. In other words, functions that have a power series expansion that go like 1 plus x squared plus x to the 3, etc. But I'll make this a little bit clearer just now. Is everybody with me?
Yep, still good. Good.
Okay. So of course, we don't want our answer in terms of phi. We want our answer in terms of the original wave function psi. So in terms of the original function, psi of z, our solution reads A, same integration constant, z minus 1 over square root of z times 2f1 of a half minus k, a half plus k, minus a half z plus b times z minus 1, 2f1 sorry, just yeah, okay, 2f1 of 2 minus k two plus k, 5 halves, and z. Okay. Now, the general solution has two constants of integration. These constants of integration, as normally happens for differential equations, can be fixed by boundary conditions, by boundary data. In this case, the boundary data comes from physical considerations. We are, of course, trying to solve a physical problem. We have some molecule, and we're modeling the vibrational excitations of this molecule. And so the boundary conditions that I need to impose is that at z equals 0, the wave function stays finite. So psi at 0, I want to be finite. I don't care how big it is, as long as it's not infinite. And this necessarily implies that my first integration constant must be 0. Okay, so that's fixed one of them. excellent. And I can always normalize the second one to 1. So normalizing second one, b, to 1, we get that our wave function psi of z is z times z minus 1 to f1 of 2 minus k, 2 plus k, 5 halves, z. Okay. So you might object and say, well, you can't just normalize the one variable, the one integration constant. Surely you need to apply 2 boundary conditions in order to determine both of the integration constants. Here we have the boundaries set at z equals 0 and z equals 1. And so a perfectly natural question to ask is, what happens at z equals 1? So it turns out that if we apply z equals 1, when we apply boundary condition at z equals 1, we'll find that the geometric function actually diverges at z equals 1. However, divergences are not a bad thing. In fact, it turns out that understanding how the geometric function, the hypergeometric function, diverges will allow us to figure out what the eigenvalues of the energy are. So the first thing is I go to, the question I'll ask is, what about boundary condition at z equals 1? Key point here is 2f1, the hypergeometric function, diverges here, and we need to understand how it diverges. So now I need to write some identities down, and these hypergeometric functions are like any special function that you encounter. Somebody has studied the hell out of them and wrote down a whole bunch of identities that we now just use. So to understand how the hypergeometric function diverges, I need to resort to some of these identities. Fortunately, you can find them in any table of integrals and functions, so special functions, so you can go look them up. But the identity that we are going to need is the following. So to understand how it diverges, we first note that hypergeometric function satisfies the following. 2f1 of a, b, c, and z for some parameter set a, b, and c is gamma. This is the gamma function of c, gamma c minus a minus b over gamma of c minus a, gamma of c minus b, times 2f1 of times 2f1 of a, b, a plus b minus c and 1 minus z. Do I have space? Okay, plus 1 minus z to c minus a minus b times, so I'm going to go to the next line. That's what that means, okay? Times gamma of c, gamma of a plus b minus c over gamma of a, gamma of b times 2f1 of c minus b, c minus a, c minus a minus b, sorry, plus 1, 1 minus z. Okay, it's an obscure identity, but it's one that's going to be important for what we need. In particular, if I take this identity, substitute into the expression for the wave function, we'll find that, I needed a page, we'll find that is everybody, can I go to the next page? Is anybody still copying down anything?
Yes. Give me 10 seconds.
Go. Okay, so while Kiniso is copying down, what we do now is we substitute this expression into the expression for the wave function that we found. And we want to explore what happens near z equals 1. Kiniso, can I go along?
Yes.
Okay, so what this means for the wave function is that psi of z is equal to z times z minus 1 times gamma of 5 halves, gamma of 3 halves, 2f1 of 2 minus k, 2 plus k, 5 halves, 1 minus z, all over gamma of a half minus k, gamma of a half plus k, plus, or rather minus, z over the square root of 1 minus z. Somebody is not muted. Gamma of 5 halves, gamma of 3 halves, 2f1 of a half minus k, a half plus k, minus a half, and 1 minus z. Sorry for squeezing it in there. All over gamma of 2 plus k, gamma of 2 minus k. And now we can see exactly where the divergence comes from. As z goes to 1, the square root of 1 minus z in the second term goes to 0. And so in order to have a finite, finite psi at z equals 1 requires that gamma of 2 plus k times gamma of 2 minus k go to infinity. In the denominator, that infinity in the denominator will cancel the 0 and make sure that the term goes to the second term, doesn't give me any contribution, and so that I have a finite wave function at both boundaries. And this gamma function product blows up if the gamma function product blows up if 2 plus or minus k is minus some integer, because if you recall, what happens to the gamma function is that it blows up at each value of its argument being a negative integer. Okay, expanding in terms of the energies, this is the statement that 2 plus or minus the square root of 1 plus e, the energy eigenvalue, must be a negative integer, which then necessarily means that the energy eigenvalues are quantized as n plus 2 squared minus 1 for n equal to 0, 1, 2, etc. And this is how the divergence in the hypergeometric function allows us to work out the energy eigenvalues of the Schrodinger problem. Any questions? There are a bunch of steps that I have skipped in going from phi to psi. Yeah, thank you. There are a bunch of steps that I've skipped in going from phi to psi, etc. That is a very valuable exercise for you guys to fill in the gaps, and I'm going to leave those gaps to be filled in for you. Okay, you know what you're shooting for, and it's definitely worth your while to make sure that you can figure out all of the factors that sit in here. Okay, so that's it. That's how you work out the molecular vibrations, the vibrations of molecules by modeling it as a Push-Teller potential. Now, let's return for the last 20 minutes of the class to the problem that we started trying to solve, which was so returning then to our original problem. So from the last time, we said that having now motivated why the hypergeometric equation and its solutions, hypergeometric functions, are in fact important things to study, let's recall what we were doing. We were studying the second order differential operator, Lz, which I said was called the hypergeometric operator. And this hypergeometric operator now should look familiar. It's the operator that we ended up with in trying to, well, once we made the change of variables in our last problem. And it looks like this: z times 1 minus z, d2 by dz squared, plus this gamma minus alpha plus beta plus 1 d by dz minus alpha beta. Okay, so we want to study this operator, and in particular, we would like to get an integral representation for the solutions of the hypergeometric equation. So why is this different from what I just did? Well, what I just did had an expression for what I just did had an expression for the solutions in terms of these hypergeometric functions. My statement here is that I can write these hypergeometric functions in general as integrals over some set of simpler functions. If I can do the integration, then it will converge to precisely these hypergeometric functions. But there are some times where I can't do that integration. Nevertheless, I can read off the properties of the solutions of the hypergeometric equation by studying just those integrals. So in particular, one would encounter this in the study of conformal field theories, where you either in string theory or in condensed matter physics, where these things crop up near what are called quantum critical points. You get these conformal field theories, and conformal field solutions of the conformal field theory equations can typically be cast in terms of precisely these integral representations of the hypergeometric equation. So our goal here is to work out an integral representation of the hypergeometric equation, and recall that, let's go back to what we were doing. Recall that what we wanted to do was take this ansatz for the solution to the equation of the form Lz acting on u equal to 0, plug it in, find another operator, m, related to L by the fact that they act the same way on the kernel of the differential of the integral representation, this integral kernel, and then then solve the associated equation, which we got by integration by parts. Solve the associated equation, mt dagger acting on v equals 0, together with this boundary condition constraint, q equal to 0, and hope and pray that the solution to this equation is simpler than what we started off with. And then I said the last time that the whole name of this game boils down to choosing the appropriate integral kernel. If you wanted to solve the second order wave equation, for example, or the heat equation, or Laplace's equation, and you wanted to solve it by integral equations, then you would choose as the integral kernel the Fourier kernel or the Laplace kernel. And you would do this because they simplified the problem significantly by converting it from a differential equation in X space to an integral equation in K space. To an algebraic equation in K space. If they converted it into an integral equation, you'd be screwed. But at the end of the day, it comes down to an appropriate choice of kernel. So we started off by thinking about this differential operator, the hypergeometric operator, and we said that because the coefficients are polynomials in Z, it would make sense to choose a polynomial in Z to be the integral kernel. And so we chose this Euler kernel, k of zt equal to z minus t to the s. Okay, so that's where we left off the last time. And then, well, that wasn't quite where we left off the last time. The next thing we needed to do was figure out what happens if we act with this L of z on the kernel. And when we act on L of z with the when we act with L of z on the kernel, we get 3 contributions. They each enter like something times z minus t to the s minus 2. If I manipulate the products sufficiently, so here I pulled out a factor of z minus t, here I pulled out 2 factors of z minus t. In each case, what's left is something that goes like z minus t to the s minus 2. So that the action of L looks like this complicated mess. Okay, but we still have to pick another operator m such that Lz acting on k is the same as mt acting on k. And I said that one way to do this is to exploit the symmetry of the kernel. So in this case, I notice that if I exchange Z and T in the expression for the kernel, that all that happens is that it just pulls out this factor of -1 to the S. So that tells me that perhaps I might go looking for an M that has a similar form to L. And the reason for this is because the equation that determines M is that LZ, so this operator L acts with respect to Z, acting on the kernel, must be the same as M with respect to T acting on the kernel. So that's why the symmetry is telling me to go looking. And so I say, well, let's take a chance and say that MT is some polynomial times the second derivative in T, plus some polynomial times the second derivative times the first derivative in T. And I'm not going to include any constants here. This might be wrong, and I might need to revisit this, but I'm going to take a chance and hope that I end up with a simpler operator. Okay, is the strategy clear? Okay, good. So I'm not going to assume that there's any constant terms in here, and my job is going to be to figure out what P1 and P2 are. So the way I do this is by acting with this M on the kernel, and then equating it to this expression here for LZ acting on the kernel. Okay, so if I do that, I find the following to be true. So here, my statement is that LZ acting on K, so LZ acting on K is the same as MT acting on K, if and only if the following holds true. Following three equations hold. The first equation is that minus S times S minus 1 minus S times alpha plus beta plus 1 minus alpha beta must equal to 0. The second equation is that minus P1 times S is equal to S times S minus 1 plus S gamma plus ST times alpha plus beta plus 1 plus 2 alpha beta times T. And the third equation that needs to hold is that S times S minus 1 times P2 plus P1 times S times T is equal to minus gamma times S times T minus alpha beta T squared. Well, it's not too difficult by looking at these equations to see that the first equation requires that either S equals minus alpha or S equals minus beta. It turns out that both of these conditions give the same representation. So just for definiteness, let's say that S equals minus alpha. So you can substitute that in there and you can see that that equation is solved. So again, S equals minus alpha and S equals minus beta both solve the first equation. So we're free to choose, both solve the first equation. So I would, in principle, choose S equals minus alpha, go through this and solve for P1 and P2. S equals minus beta, go through it and solve for P1 and P2. And I'll find that I'll get the same P1 and P2. So I'm going to, for definiteness sake, choose P1 and P2 to be, choose S equals minus alpha. Okay. You should, of course, not believe me and go ahead and check for yourself. But the remaining equations can be solved for the coefficients. So these two equations then lead to the fact that P1 of t is equal to alpha plus 1 minus gamma plus t times beta minus alpha minus 1, and P2 equal to t times 1 minus t. Okay, so again, alpha, beta, and gamma are parameters. They're not independent variables. So P1 and P2 are really only functions of the independent variable t. And together, or all together, these statements lead to the fact that the operator we're looking for, mt, is t times 1 minus t times d2 by dt squared plus alpha plus 1 plus t times beta minus alpha minus 1 times d by dt. Right. So we got away with not having any constant.
I'm sorry.
Yeah.
There's a missing minus gamma term in P1.
There's a missing minus gamma term in P1. You're quite correct. Well spotted. Minus gamma. So that's alpha plus 1, right, plus t times beta minus alpha minus 1 d by dt. Cool, thank you. Okay, so this is the operator we were looking for, and we got away with not having a constant term, so it's not that much simpler, but it's sufficiently simpler that I can solve the problem. I can get an integral representation. Okay, so all right, so let's stop there for now, and then on next week we'll finish the problem, and I'll show you how the representations, not only can we get a representation, but how these representations depend on the contour that we choose to integrate over, because implicit in all of this is the fact that when I write down my ansatz here, I do an integral over a particular contour on the complex plane. So the question is, how does my integral representation change if I change the contour of integration? So that's what we'll study next time. Any questions? Okay, good. So I will see you guys again next week.
Thanks, Prof.
Thank you.